Hello, esteemed colleagues, researchers, and distinguished guests. I am from the Industrial University of Ho Chi Minh City. Today, I am honored to present our research titled An Enhanced MPPT Algorithm for Photovoltaic Systems Using Fuzzy Logic Control. To begin, let's quickly look at our agenda. We will first discuss the motivation for our study, then move into the theoretical background and methodology, followed by our key results, and finally, our conclusion and recommendations. Starting with the introduction, the main problem is that solar panels do not operate consistently. Therefore, we absolutely need MPPT algorithms to ensure we extract maximum energy. However, as we know, the traditional methods often suffer from slow speed and cause the power to fluctuate. Consequently, our main goal was to create a better MPPT algorithm using fuzzy logic control, specifically to achieve faster tracking and superior stability. Our focus was on a variable step size P&O algorithm integrated with FLC, tested in a MATLAB Simulink environment. Moving on to the theory, we must first recognize that PV systems are complex because their power and voltage curves change significantly based on sunlight and temperature. Because of this, MPPT is essential for finding the maximum power point under any condition. While classical methods are simple, they are too slow and unstable when conditions change. Therefore, we opted for fuzzy logic control because of its strong ability to handle these nonlinearities without needing a detailed mathematical model. This brings us to the literature review. Past research confirmed that FLC performs well. However, a critical research gap exists. We needed a hybrid method that could combine the stability of fuzzy logic with a variable step size approach within the P&O framework. The ultimate goal was to ensure both rapid transient response and high stability. Let's now detail our method. We conducted a quantitative simulation using MATLAB Simulink. Our system uses a Mamdani type FLC integrated with the standard P&O algorithm for adaptive tuning. The FLC has two key inputs. Firstly, the error E, which is the slope of the PV curve, and secondly, the change in error CE, which shows the direction of movement. Based on these inputs, the output adjusts the converter's duty cycle. In terms of design, we used 7 membership functions and a comprehensive 49-rule base. Now, let's analyze the results. Figure 1 shows the PV power response. As anticipated, the PV power decreases as irradiance drops. Crucially, the convergence speed is significantly fast, reaching stability in approximately 45 milliseconds after each major transition. Furthermore, examining the duty cycle, we can see the adjustment is smooth and monotonic, successfully eliminating the oscillation found in fixed-step methods. More compellingly, the raw error signal quickly returns to zero, confirming successful MPP tracking. Finally, comparing our performance metrics. The proposed FLC P&O achieved a convergence time of only 45 milliseconds, compared to 200 milliseconds for the old P&O, making it over 4 times faster. Moreover, the power ripple was less than 0.5%, which is 5 times lower than the old method. Overall, tracking efficiency reached 98.8%, a significant improvement. In conclusion, the enhanced MPPT strategy successfully integrated FLC with the variable step size P&O, achieving notable improvements 2-4. Specifically, convergence occurred in less than 45 milliseconds, and stability was excellent with a power ripple below 0.5%. Our contributions are twofold. Theoretically, we confirm this hybrid technique is ideal for practical PV systems. Practically, our approach has low computational complexity and is robust, making it highly suitable for real-time implementation. However, there are still limitations. Our focus was primarily on rapid irradiance changes, meaning performance under partial shading conditions was not fully explored. Also, the evaluation was based solely on software simulation. Therefore, we recommend 3 key areas for future work. First, hardware implementation and testing. Second, integrating FLC with global MPP search strategies for better PSC performance. And finally, conducting a robustness analysis under sensor noise. Thank you very much for your kind attention.